Okay, last chapter, 14, it's exponentials and logarithms. It's another one of those chapters where it's only year 12, there's nothing in year 13 about exponentials and logarithms. I mean, there's a little bit in stats, but it's just this stuff again. Very similar to the stuff there. Let's get into it. So the first thing I've written down here is just the basics of logarithms. So if you've got a to the n equals b, you can rewrite that as a logarithm, and vice versa. So if you've got a logarithm where there's only one log, you've got the base, you've got what's being logged, and you've got an answer, you can rewrite that in the exponential form, or you can rewrite the exponential in the log form. So being able to do that in both directions is very useful depending on what you know. Do you know this, or do you know b? You should have the base. But you'll either not know b or you'll not know a, and whichever form is better for finding out that solution. So if you don't know b, this is the form you want it in. If you don't know n, this is the form you want it in. Moving on, exponential. So e is just like what's it called? Irrational number like pi. It's a special number such that when you differentiate e to the power of x, you get e to the power of x. It doesn't change. So e to the power of kx is k e to the power of kx. You see the e to the power of kx bit doesn't change, and you just multiply by the power. The coefficient of x. So you bring that coefficient down, multiply by it, but this bit doesn't change. And if there was no coefficient, if it just said e to the power of 1x, that would just be differentiated to e to the power of 1x. So nothing would change. These are your laws of logarithms. So if you are adding together two logarithms with the same base and the coefficients are both 1, then you can just multiply the b and the c together. If you are subtracting them, then divide the b by the c. Again, I'll point out you have to have so the coefficient needs to be 1. You can't have like one of these say 2 and the other one say 1. If you do have that, then use this law at the bottom before you do the subtraction or the addition by either, so normally you'd have it in this form, n log, so if it said like 2 log base 10 of 5, you could bring up the n as a power, so you could have log base 10 of 5 to the power of, I can't remember what I said, but you bring the n up as a power instead. So you always use this one before using these two, if you're trying to combine logs together. Last thing I've written down here is just the nature of the natural logarithm. The natural logarithm is purely a logarithm with base e. And it's the same e as this one. It's that surd, that irrational number. And we normally don't write log base e, we write ln, the natural logarithm. But it's useful to know that, so that when you have questions like this, you know what the base is. The base is e, and so that's how you would get out of having log. Right? If you wanted it to be an exponential, the base is e. Okay, intermediate stuff. We've got solving logs, or solving log equations. Now, there's like a process you want to use for solving log equations. The whole idea, like solving normal equations, is if you've got multiple terms, you want to kind of combine those terms together to simplify it. With logs, you want to combine your log terms together to simplify it. So the way to do that, as I said before, if you've got subtraction here, you can only do that if these two have they have a coefficient of 1. Right, so 2 in this is a 1, not okay. So first thing you want to do is put the 2 as a power. So use the power law, this one down here, put the 2 as a power. Once you've got them both to have a coefficient of 1, then you can do the subtraction. It's called the division law. You do x squared divided by 5. Just make sure that the bases are the same, and that is perfectly fine. Once you've got it in this form, this is what you're aiming for logs. You want to combine them together, so you've just got the 1 log. Right? It just says log once. Once you've got 1 log, then this is the stuff you need. So this is your base, that's the power, and that's the answer. So 3 to the power of 4 equals x squared over 5. 3 to the power of 4 equals x squared over 5. Okay, so get rid of the log at that point. 3 to the power of 4 is 81, so times that by 5, and then that's equal to x squared, square root it, and that'll be your solution. You can always check it by putting it back into the original equation, but the process is powers first, then do your subtraction, the division law, the multiplication law, whichever one it is, until you've only got one log. Then use the nature of logs to rewrite it as an exponential and solve it the way that you would normally solve an equation. The last thing I'm putting in the intermediate is they tend to have a few of these questions. I've seen them come up more than once, so I thought I'd mention it, where it just says like, let p equal some log, and then to write something else in terms of p. And I see people make mistakes on this all the time. You just use the log laws, right, to write this. Like you want to split up anything which is not in p. So this is log base 4 of x. Here it's log base 4 of 16x. So you want to split that up, so it's log base 4 of 16, add log base 4 of x. It's using this law here, but kind of backwards. So write that as log base 4 of 16 plus log base 4 of x, and then log base 4 of 16 is 2. Anything with just numbers in it and no letters is just a number. Sometimes it's a whole number like this, it's 2. Sometimes it's a irrational number, but it is only a number. So you can either keep it in exact form. I'm not talking about this question's done. But in a normal question, sometimes you end up with log base 5 of 2 or something, or log base 7 of 19. Those are just numbers. They're just irrational numbers. So I like to keep them as, their exact form, log base 7 of 19. But if you're giving your answer to decimal places, feel free to just put it into your calculator, get it as a decimal, and then just work in decimals. Alright, last stuff is advanced. We've got, this is to represent exponential modelling. Okay, so there's a couple of things I'd like to point out about exponential modelling. You've got two different types of exponential model. You've got exponential growth, where your power is positive. So you've got something in the form of y equals e to the x. Like something will be multiplied, you'll have like maybe y equals a e to the kx plus c, but it's a positive coefficient of x, so that means it grows. The other one is when you have a negative coefficient of x, and that decays. So a lot of the time having an understanding as to whether it's growing or decaying just helps you get started with the question. I've put an example here of a kind of question that you, a kind of model that you might have. I don't know what p would be. But it doesn't matter because it's the general shape that you're looking for. A couple of things always come up with modelling. So initial values is when t equals 0. A lot of the time this is a time situation on the x-axis. So if you're looking for the initial value of something, or the initial population, or the initial whatever the model is about, t equals 0. Now exponential models differ from, say, straight line models or quadratics, because when you put them as t equals 0, the term disappears. But with these, because it's a power, putting it as 0 means that it doesn't disappear, because e to the power of 0 is 1, so you still have that. So here the initial value would be 100 plus 50. Excuse me. If you've got a number on its own, that's the asymptote. Okay, because this number here, this is exponential decay that's got a negative coefficient, and it's going to get smaller and smaller and smaller, but 50 is going to stay as 50, so that's going to be your asymptote. Excuse me. So yeah, be aware of the asymptote. The initial value is going to be 150. Not even on the screen. There we go. And then, what was the other thing I was going to say? If it talks about rate of change, if it ever talks about the rate of change being something, then you're not going to substitute into this equation. You need to differentiate first. Now this differentiates really easily because you just multiply by negative a half, so you get negative 50 e to the minus a half t, and then that one disappears. So if it talks about rate of change, you want to differentiate first. Other than that, if it gives you a value in a question, like in the part question, say you've got to part C and it says something about a value of either t or of p, just substitute that in and solve it. That's the same with any model though. If it gives you a value in a part question, substitute it in and solve it. The only thing that's a little bit different with exponentials is it says rate of change, then you're going to have to differentiate and then substitute it in. And then the last bit, anything which is in this form, so your variables here are n and t, and a and b are constants. So anything in this form where you have a variable which is related to t in a kind of exponential way, you can make this into a straight line graph, sort of like you can make it look straight by taking logarithms of both sides. So it will look like a straight line, and you can get information from that straight line graph by relating it to y equals mx plus c. So the way that you would do that is by taking logs of both sides. So take logs of n, take logs of a, b to the power t. Use your log laws to split the a from the b to the power t. They're times, so it becomes plus. And then bring the t down as a power before, and I've not done all the stages because I was running out of space. But if you follow those stages through, you end up with this, the log a plus t log b. Now the reason why that's good is because if you plot log n as your y-axis, that's one of your variables, and you plot t as your x-axis, that's the other variable, then you end up with a straight line where the gradient is the thing that's multiplied by the x-axis thing. So log b is the gradient, and log a is the y-intercept. So you can work out what the values of a and b are by making them equal to, or making log of them equal to the y-intercept and the gradient. So this is one of the ones that's more tricky. These are doable if you remember your kind of modelling mantra, the things that always happen in modelling questions. If you don't know what to do in one of these questions, where it's got some kind of straight line but then it's also got an exponential function, take logs of both sides. When it says log, by the way, like this, with no base, it just means log base 10. It's just your standard log, because we work in base 10. Anyway, take logs of both sides and then use the log laws to try and get it into the right form by remembering to, you can't bring down the t. If I take log of this side, I can't bring down the t to the front because a is not raised to the power of t. So first I've got to split those up and then bring the t down. And it's only 2 stages to get to there, but I don't know, it seems to confuse some people. That's why I've put it in the advanced, because it's kind of maybe an A grade thing. I think that's it. I think maybe I rambled a little bit there and coughed a bunch, but enjoy.